Math 114, quantitative reasoning. It's time for the final test of the semester, and it's time to review for test 3. Determine which ordered pairs satisfy the given equation. Okay, so there's 3 ordered pairs. What we're going to do is we're going to recognize that the first number in each one is an x, and the second number is a y. And if they satisfy the equation, that means if I plug them in, I should get something that's true. So we're going to try that. The first number I'm going to plug in is 6/5. I'm going to plug that in for x, so it's 5 times 6/5 minus 3 times 0 equals 6. Well, what do I get? I get 6 equals 6. Does 6 equal 6? Yes. So that works. I can try 3, 3. And what would I get if I calculated that out? I get 15 minus 9, which is 6. And the other side is also 6. So that works out. So both of those work. Let me try the last one here because we can pick more than one answer on this one. And we've already picked 2. Maybe it's all 3 of them. So when we do the last one, we see 5 times, well, x is 0 this time, minus 3 times negative 5 this time equals 6. And obviously this one, well, that gives us something like 15 equals 6. Does 15 equal 6? No. So this is not our answer. So we can say, not this one, but the other 2 work just fine. Let's consider this graph, okay? So this is height and shoe size. And if we could try to describe what's happening here, what we're seeing is that as height increases, shoe size increases. And it says it's linear, right? It's a straight line. And so basically, as you get taller, your shoe size increases. Now that basically makes sense, except let's take a look at the slope. Now the slopes we can find by looking for rise over run. So I'm going to find 2 nice points. That's a point right there at 0, 1. And then I'm going to go up. And I think I see a nice point right here. So I'm going to go with that one. And you see that my second point that I have is at 30, 5. Okay? And so I really don't have a problem with these predictions other than if you really were 0 inches, then your feet wouldn't be shoe size 1, they'd be 0. But let's go ahead and use these 2 points to find our slope. Slope is change of y over change of x. So the y's go up 4, and the x's go up 30. And if we were to simplify this a little bit, we get 2 over 15 as our slope. Okay? And we could then say, as a rate of change, we could reword it because rate of change is to say we go up 2 shoe sizes for every 15 inches. So in other words, for each 7.5 inches, shoe size increases by 1. Find the slope. Now the slope is the change of y over change of x. In other words, we're going to say delta y over delta x is our slope. And so we're just going to say how much did the y change? From negative 10 to 9, it went up 19, okay? So the change was up 19. And from 2 to negative 3, how much did the x change? It went down 5. We're going to simplify that a little bit. I'm just going to put negative 19 over 5 because it doesn't simplify much. And that's my slope. Find the slope. When we look at each of these, okay, what we want to do when we're looking at a graph and we're finding slope is first find 2 nice lattice points. In other words, we want to find 2 points that our line goes through an exact, like, pretty point. And so I've got a couple here. I can see that this one goes through there, and I got one there. And so the way we do that, I can see the other graph. There's more than one right answer when you're picking these points, but I like to pick 2 points that are really close together. In other words, I could pick maybe this one way down here but I like to pick ones in the middle and pretty close together. And so the next thing we look at is slope is the change in y, or it's also known as the rise, and then the change in x, or the run. So how much does it go up and over? So the slope here goes up 3 and over 4. So that's our slope. And the other one, what we see is the slope actually goes down 3 and over 1. So our slope is going to be -3. An airplane's altitude declines steadily by 27,600 feet over a 16-minute period. Find the rate of change. So altitude per minute is what we want, the rate of change. So that means per minute, we're going to put minutes on the bottom. So we're going to say 27,600 feet over a 16-minute period. And all we have to do is divide that, because per minute means we want to go ahead and say, yeah, how much would it be on average for just 1 minute? So once you type that in your calculator, you're going to get an answer, and that is the final answer. For the spring semester, let's say part-time students at a certain community college paid $442 per credit, okay? But they also paid a fee of $30 per semester. So if we're going to come up with an equation for this, we'd say the tuition or total that they're going to pay is the $442 plus that $30 fee. But the problem with that is, notice that that's just two numbers added together, okay? So we actually have a linear model here where we have something that varies. They're not all going to pay the same amount, because the more classes you take, the more you're going to pay. And so our linear model has to make sure we choose which one we're going to multiply. As it increases, we're not increasing the student fee, we're just increasing the tuition cost, which means we have a slope right there. And that's showing us the increase or the cost per credit. Two sets of points are described in this table. Finding the equation of a line that contains the points. Okay, so two separate points. And so we got a couple things that I can notice. One is that we can use any 2 points in the table to find the slope. So I'm going to start with set 1. And I have the slope should be the change in y over the change in x. Now, how much did the y change? The y changed between those first 2 points that I chose. It went up 4. How much did the x change? The x went up 1. And so if I were to simplify that, I get a slope of 4. The other thing we need, if we're finding an equation of a line, if we're going to put it in y equals mx plus v, we need the y-intercept. The y-intercept is when the x is 0. Now, I actually do know the y-intercept. The y-intercept, in this case, is 5. So for set 1, we get y equals 4x plus 5. We can do it again with the other set. If we look at the first 2 points to find our slope, how much does the y go up? The y actually goes down 5, and it goes, the x is only changed 1. So I'm just going to say our slope is -5. And if we look for b, our b is 10, because when y equals 0, or when x equals 0, the y equals 10. And so we can go ahead and write our equation. Y equals -5x plus 10. Water is steadily pumped out of a flooded basement. Let V be the volume in water. And so we've got this graph. So the first question is, how much water is in the basement after, let's just say, after X hours of pumping, okay? So let me give you one. Let me say after 6 hours of pumping. After 6 hours of pumping, how much water? So we go to that and we see, oh, 6 hours of pumping is right there. That matches up with 4,000 gallons left over. There's a lot of water in there. After how many hours of pumping will thousands of gallons, will 1,000 gallon remain? Okay, so this one's a bit tougher, but if we notice this is linear, where would 1,000 be? It wouldn't be right there. because that'd be 2,000. It'd be right halfway between right there. So we're going to say after how many hours? 6 hours and 45 minutes. That's what I'm going to say. Or 6.75 hours. How much water was in the basement before any was pumped out? So after 0 hours of pumping, we had 28,000 gallons. After how many hours of pumping will the water be pumped out? So when do we get to 0? And it looks like after 7 hours will be empty. Maybe not dry, but definitely empty. Let V be the value of a car when it is T years old. Some pairs of values of T and V are listed in the following table. So we have T's and V's, and we want to create a scattergram of this data. Now I'm going to tell you right now, what is a scattergram? A scattergram is a plot that shows what's happening in this data. And so this scattergram might look something like this. I want you to notice a few things about scattergrams. They're not always going to line up perfectly. Okay, and we can actually make scattergrams by going into Excel. Oh, that's not how you spell Excel. Excel, or we can use Desmos. And either one allows us to take a table of values and graph them as dots. Okay, the reason I like Excel a little bit better is because we can also say add a trend line. And the trend line is the line in the scattergram that goes in the middle of all your dots. Notice it doesn't actually have to hit any of the dots, but it's supposed to kind of minimize the deviations. Let's say we have a hip hop band, they're playing, and the venue that they're playing at charges $6 at the door. That's their cover charge. But then the venue is also going to make money for every drink that they sell, for every Mountain Dew. So if each Mountain Dew costs $2, then every time somebody buys a drink, they're going to make $2, right? So let's look at the total cost for you to go to this concert. It could be pretty cheap. It could be, if you spend no money, okay, or if you drink no drinks, it's still going to cost you $6. So if you spend $0 on drinks, your total cost is still $6. But if you spend $2 on drinks, your total cost is, well, 6 plus 2. If you spend $3, it's 6 plus 3, or 6 plus 4, or 6 plus 5. And so the pattern really is that it's always going to be that 6, but then we add the cost we're paying in drinks. Use the slope-intercept form to graph the equation. It's not in slope-intercept form, so the first thing I'm going to do is subtract 2x from both sides. And I get y equals negative 2x plus 1. My slope is negative 2. My y-intercept is 1. So I'm going to start by graphing my y-intercept. I'm going to go to 1. And then I'm going to move according to my slope. It says go down 2. 1, 2. And then I can't just put a point there. I need to move over. So if we don't have a denominator that tells us rise over run, we just move over 1. So I'm going to put my second point right there, and then I'm going to connect my dots. Decide whether the following statement makes sense. When I graphed a linear function, it turned out to be a wavy curve. Does that make sense? No. Linear functions are lines, particularly straight lines. You run along a path at a constant speed of 2.4 miles per hour. Okay, so you're going just straight 2.4 miles per hour. So after 1 hour of running, you've gone 2.4 miles. Right? If we stop right here, we'd be at 2.4 miles. But you kept running. You actually ran an extra bit. So you actually ran longer than that. And so this is going to be not too bad, because when we do rates, what we're saying is, I already know the rate, 2.4 miles per hour. And I'm traveling for 1 hour, it'd be 2.4, but I'm traveling for 1.3 hours. And so that's going to give me my distance, my total distance. Okay, and you could also do it with the 2.4 and the 3.4 hours and multiply them together to get your distance. A snowplow has a maximum speed of 35. It can't go more than 35 because it's probably got like safety features, and also it's a snowplow, so it's very big. It does get slower though. As the snow increases, the snowplow has to go slower to remain in control and do a good job of snowing or plowing the snow. So at what snow depth will the snowplow be unable to move? So let's run some numbers here. First off, if there is, let's say depth of snow was 0. So if there's 0 snow, what is my speed? I'm going to use, let's use S for speed. That's an S, okay? Then we'd be going 35 miles per hour. The follow-up would be, what if there was 1 inch of snow? Now, according to what it says up here, it says its speed decreases 1.5 miles for every inch. So we're going to take that 35 we had minus 1 times 1.5. We could keep doing this, and we could put 5 inches of snow, and we just calculate it the same way. We would have to say the S is 35 minus, well, this time it's 5 times 1.5. And so we actually have a linear model here. We have a linear model where S equals 35 minus 1.5 times the depth of snow. Suppose your dog weighed 1.9 pounds at birth and 14.9 pounds 1 year later. So at birth, so we're going to just kind of make a little bit of table, X and Y, where X is how old they are. So at 0 years old, they weigh 1.9 pounds. And 1 year later, so at 1 year, they weigh 14.9 pounds. Based on those 2 data points, it actually asks us to go ahead and assume we can use just those 2 data points and assume we got a linear function. Okay, so we're going to do slope by looking at those 2, and that means we're going to do the change in y over the change in x. Okay, so when we look at the 2, how much did y change? Y went up 13. How much did x change? X only went up 1. So our slope is 13. The next thing we need is we need our y-intercept. So our y-intercept, in this case, it's when the x is 0. So in this case, it's 1.9. We have it right there. So we can write our function as y equals 13x plus 1.9. The next thing he says is use this function to predict your dog's weight at 4 and 11 years of age. In other words, we should be able to use that function to plug in 4 and see what we get. We could also plug in 11 into our function and see what we get. And after we do that, we'd be able to kind of see whether our model makes sense. So let's say, for example, if we plugged in our numbers and we said that eventually your dog is going to weigh negative pounds, that doesn't really make sense. But also it wouldn't make sense if we said that your dog's going to weigh 1,000,000 pounds. So there's some things that we could watch out for that would say, you know what, this model isn't very good when we get big numbers. Use the slope and the point containing the y-intercept to graph the line. And so we have the slope, it's right there. We have the y-intercept, it's right there. So the y-intercept is that -10, which means we have a point 0, -10. And so if we're going to use those to graph a line, all we have to do is start at the y-intercept, start at 0, -10. And then we move according to the slope. So I'm going to go up 5 from there, and then I'm going to go over 1. Up 5, over 1. I'm trying my best to draw a straight line. And that's all we have to do. Find an equation of a line that contains the points listed. And when we look at this, we could come up with this off the top of our head, but I'm going to use the method we've used on other problems on this review. So when we look at these 2, we have 2 points right there, okay? So I'm just going to use a linear model. It says find a line, so I'm going to say delta y over delta x, and I'm going to find my slope. So how much does the y change? It goes up 1. And how much does x change? It goes up 1. So what's our slope? Our slope is just 1. The next thing we need, if we're going to write it in y equals mx plus b, is we need the b. Now the b is the y-intercept, and that's also given to us. It's right there at 0, 3, which means we can then go ahead and write our equation. Y equals x plus 3. Find the x-intercept and the y-intercept, and then graph the equation. Okay, so to get started, we need to recognize that the x-intercept and the y-intercept is when we have zeros for one of our two coordinates. So we're going to plug in 0 for the x and find out what the y would be. And then let's plug in 0 for the y. So it's not too bad to find x and y intercepts, because we plug in 0 and then we just get 4y equals 12, and so y equals 3. If we do the reverse and we plug in 0 for the y, this part goes away and we just have 3x equals 12, so x equals 4. And so all we have to do is then graph those and connect the dots. But it is important to pay attention to which one's the x-intercept and which one's the y-intercept. This one is the y-intercept, because the y-intercept has a y value, but it doesn't have an x value other than 0. And this one's the x-intercept. Cost of publishing a poster is $4,000 just for setting it up. But then each poster costs you $4. So if you were to try to print just one poster, it would cost you $4,004. This is a linear function. It's a linear function because we have a rate per, that's a straight line, and we also have a startup cost, okay? And so our function could be said to be y equals 4x plus 4,000. Now the independent, what's going to be determining your cost is how many posters you have. So that's your independent, the number of posters you print. And then the more posters you print, the more it's going to cost you. So that's your dependent variable. That depends on the number of posters. Finding the equation of the line that contains the given point and is perpendicular. So first off, when we have this line, a line that's perpendicular has not the same slope. The slope of this one is -11, but a perpendicular line has the slope of 1 over +11, okay? So a perpendicular slope has the opposite reciprocal slope, which means I want an equation like y equals mx plus b, but I want my m, because I want it to be perpendicular to that one, to be 1 over 11. Okay, that's great and all, but I still don't know what b would be. Now, since we were told it has to match that point right there, then we know in x and y we can plug in. So I'm going to just plug those in for x and y. Make sure you put the x with the x and the y with the y. So that's going to be 11 equals 1 over 11 times -10 plus b. And if we're going to go ahead and solve that, then I get 11 equals -10 over 11 plus b. 11 plus 10 over 11 equals b. And so b equals 11 point, that's like 11.9. Okay, I rounded a little bit there. So what does that mean? That means I can now write my equation as y equals, I probably shouldn't use decimals. Let me be more precise. So that's 131 over 11. I just multiplied 11 times 11 and added it to 10. So I'm going to leave it as a fraction, just to be more precise. And I get my equation. Let P be the percentage of dentistry degrees earned by women, okay? So T equals 0 actually represents the year 1970. And so it says, hey, try to create a scattergram, but we have to change a couple things about this. One is we don't want to graph the X to be 1970. We want to change this up. So I'm going to have another column here. We're going to do this in Excel, because remember, we can do scattergrams in Excel. And so in my first column, I have the years, and then I have percents, but I'm going to put a column in between there, which is my T. it says the t for 1970 should be 0, 1980 should be 10, and so forth. So we should get 20, 30, 40. And it says create a scattergram. And so we're going to select these two, and we're going to go to Insert, Scatter Plot. And then, because it wants us to draw a line, when we look at that scatter plot of all those dots, we're also going to make sure we insert a trend line. And that inserted trend line might be under Add Chart Elements. The average length of a 6-year-old fish is 27 inches. And this is a linear model, so we say a 6-year-old fish. So year 6 and length is 27. So the next one it says is, well, we got a 21-year-old fish, and that's 54.3. So what it says is try to come up with a good formula here, okay? Find an equation of a linear model. So what I want to do is actually, we could do this in Excel, and the way we do this is we put these in, and we insert scatter plot, okay? And then we insert our trend line. There's a bunch of other features that we can use in Excel to make this happen, especially if they were to ask us more questions like predicting certain things. We could use things like the equation forecast, which allows us to just select those and then tell it what numbers we want to put in to guess about, okay? But this is a good way to get started, and it allows us to then look at that trend line and see where the data would go in. Desmos also handles this, all right? If we put this in, Desmos as a table, and then we use the formula y, and then squiggly, mx plus b, it will graph the line, and then it'll be right on there, and it's very easy to manipulate. The catch is we need to make sure the y that we have here, like y1 or x1, matches the y1 and x1 in the table. The rate at which a cricket chirps depends on the temperature. It is possible to estimate the air temperature by counting chirps, theoretically. So what we can do is we can look at the table, and we can try to graph this and find an equation that matches this. So what we're going to do is we're going to take that table and put it in Excel. Once we have it in Excel, what we're going to do is we're going to insert a scatter plot. And then we're going to insert a trend line. And that'll give us a scatter plot with the trend line that should get us an idea of whether this actually works, whether this actually makes a linear function. Now, if we needed to forecast and do things like that, we can use formulas like equals forecast, okay? Or we can simply look at our scatter plot and see where that trend line would take us. The percentage of male workers who prefer a female boss over male boss increased approximately linearly from 6%, so 6% in 1979, and then in the year 2003, it was 12%. Okay, so I want you to notice what happened here. It took how long for it to double? Okay, so what we can do is we can start doing the rate of change, our slope. We're going to say the change in, let's do the change in y, or in this case, the change in percent, over the change in years. So if we use this change in y over change in x, but this time I just put it in the context here, what we're going to see is that we went up 6%, and it took us 24 years, which means we kind of have a slope. We can actually simplify that a little bit. M equals 1/4. So the next question says, predict when 16% of male workers will prefer a female boss. So How are we going to do this? Well, we know that it's going to go up 0.25% a year. So how much does it have to go up to 16%? That's another 4%. But we know that to go up 6%, it took 24 years. And to go up 4%, it's going to take 4 times 1/4, or 4 to the 1/4. If I divide that, is going to be plus 16 years. So we end up getting 2019. Calculate the amount of money you'll have at the end of the indicated time period. So let's say you started with 3,000, and we pay simple interest. So that means I give you 3% for 10 years. So what is 3%? We have A equals P times R, 1.03. So I'm going to make the 3% into that decimal. And then we need to do that 10 times. Okay, so since it says simple interest, when I get that, what is 3% of 3,000? Well, 3% of 3,000 is, let's see, I'm going to type it in my calculator, make sure I get it right. 90. So I'd make $90 a year. And so since they're paying simple interest, I'm just going to make $90 times 10 years. So I would make $900. It says how much money you'll have. So we won't have 900. We'll have the money we started with plus that 900. So simple interest, we find the interest for that first year, and then we just multiply that by however many years we have, because we're going to make the same amount of interest each year. Use the compound interest formula to determine the accumulated balance after the stated period. So let's try a few things on this one. So first we have the 8,000 invested. We have an APR of 8% and for 5 years. APR is annual. Okay. So they haven't told us how often we're going to compound this. So let's assume we're going to compound it annually. Okay. So we have the amount we started with, 8,000. And we're going to multiply it by 1 plus that 8%. And we're going to do that 5 times. So I'm going to put the 5 as an exponent. And what you'll get when you do this is, notice that 8% and that 1 look a little ugly when we do that. So I'm going to switch it to a single number to show you that what we have is 1.08. And as we multiply it by 1.08 5 times, we're going to get a little bit more interest each time. And so if we were to plug that into our calculator, it would give us our compound interest compounded annually. Use the appropriate compound interest formula. Now, this one actually says we have 3,000 invested for 18 years, and we have an APR. That is an annual. APR means annual interest rate. And then it says compounded monthly. So we need to do a slight change to our formula. The first thing we're going to do is we're going to keep our $3,000, and then we're going to multiply that by our 1 plus our rate. But our rate has to take into account that it's not a monthly rate. So we're going to take that 6%, which is annual, and we have to divide it by however many months there are. How many months are in a year? There are 12 months in a year. And then up top, we need to raise it to however many months we have. So rather than just writing 18, we're going to write 18 times 12. Because we have to account for the fact that we're going to calculate interest not 18 times, but 18 times 12 times. From here, we can clean it up a little bit by saying, well, that's 3,000, and the 6% divided by 12 plus 1 is going to be 1.005 to the 12 times 18. I'm going to try to do that math in my head. Hold on. That may or may not be right. And then that should give me my answer. Describe the basic difference between linear growth and exponential growth. First off, linear growth goes up in a line, and exponential growth is curved. That's the first thing. In other words, the rate of change is constant. So if I tell you I've got an investment that's going to make you $100 a year, then every year you'd expect to make $100. So that's like saying plus $100 each year. So every year you make $100. But if I told you I got an investment that's going to make you 10% per year, then what we have is in money, in actual money, then the change is changing, okay? Because I'm making a percent of my money, then the first year I make 10%, but then the second year I don't have the same amount, so I make 10% of a different amount. So the change is changing. And so that's one of the big differences with linear and exponential growth. The one that grows faster in the long run and gets really big numbers is that exponential growth. Human population has been growing exponentially for a few centuries. Do you expect this to go on forever? Okay. Do we expect to keep on going forever? What do you think? Well, I mean, eventually we would run out of room, wouldn't we? And I think that's when in the 80s, there was a bunch of movies about overpopulation. People were scared that we were going to get so many people because the population was growing so fast. But the truth is that eventually it starts to balance out because we run out of resources in space. Eventually we would run out of food for everyone, and we're already, depending on your perspective, we're already getting closer to that point. So if we start to run out of resources, what we're going to see is it's not going to grow exponentially forever. It's going to start to balance out. The other thing is we do have some ups and downs. For example, when we have a pandemic, that might change how that graph looks. Considering this case of exponential growth, okay? So you start with $1,100 per month and you get annual raises of 6% per year. So we could first write a function, and they tell us the way we write this exponential function, we say Q equals our original salary, 1,100, times 1 plus r to the t. Now, r is our growth rate, and so our growth rate in this case is 6%. Now, if we were to use this function, we could figure out things like in the year 3 years in, how much will we make? Will we still make 1,100? No, because we've gotten a raise. So what we can do is we can plug it into this formula. $1,100 times 1.06 to the third power. And that would give me your salary after year 3. Find the average price of a home in a town was $177,000 in 2007, but it's been rising 5% per year. So the exponential function, it tells us this is what we need to do. So we're going to type that in as Q equals, well, the original 177,000 times 1 plus the rate. So I'm going to write that as 1.05. And then plus, we put the t as the exponent. Great, so we have it. Now we can use this to calculate. Now obviously we put year 0, then it's obviously 177,000. But let's say we wanted to fast forward to the year 2021, okay? So then we're going to type in 2021. How many years is that? Well, that's 2021. What year is that? And t's. That's 14. So that's t equals 14. So at the year 2021, t equals 14, what would we expect the price of the home to be? Well, we're going to use the formula we have, and we're going to plug it in. I'm going to try this and see what it comes out to be. I think it's going to be a big number. Houses are expensive. And I raise it to the 14th power, and I get 350,447,8931. I got my decimal right here. So it looks like if I were to, yeah, it looks like the housing price is like doubled in 14 years. And that is it for me on this problem. Suppose the rate of return for a particular stock during the past 2 years was 5% and 35%, 5% and 35%. Compute the geometric mean rate of return. Okay, so a couple things here. One, it says the rate of return of 5%, write that as 0.05 and 35% as 0.035 or 0.35, sorry. And if we just calculated the geometric mean, we could do that with Excel. We could say equals geo mean and put those in parentheses, and it would calculate the answer. But we would actually get the wrong answer here, okay? Because just like when we look at any of the other interest or growth formulas, what we actually need to put is 1 plus r. So instead of writing 1.05, we need to write 1.05 or 1.35. And then when we calculate geometric mean using either the geomean formula or simply multiplying them together, a times b, and then square rooting them, then we should get the right answer. For the data in this accompanying table, it's asking us to calculate geometric mean. Okay, each one of these though is given to us as a percentage. Okay, it doesn't say very clearly, but it says in the problem in percentages. So each one of these I want you to think of as a percentage. So that means I also need you to think about the fact that when we're doing things with percentages and growing rates, we always use 1 plus r. Okay, 1 plus r. So that means 8.61 is actually, I'm just looking at A, 8.61 is actually 1.0861 because that's 8.61% plus 1. And so if you were to take all those numbers and take that same process, 1 plus 559, 1.1000, and 1.1851. What you get is you get the rates in a way that we can deal with, okay? Because the next thing we want to do is calculate geometric mean. You can do it two ways. I like to use Excel, so I'm going to say equals geo mean. That's the formula, geo mean. And then we just need to type in the 4 numbers, and it'll give us the answer. Only if we've already converted them appropriately. The other way to do it is to take, geo mean just means to take the root of the product. So we're going to take each of those numbers and multiply them together. And then we're going to fourth root. Why am I fourth rooting? Because the 1, 2, 3, 4 numbers, it has to match the index. So if we're taking the geometric mean of 2 numbers, we just need to square root. But if we're taking the geometric mean of 4 numbers, we have to fourth root. Compute the total and annual returns on the following investment 17 years after purchasing shares in a mutual fund for $5,900. So they paid $5,900 and then they sold for $11,100. They made some money, okay? So we're going to, how much money did they make? We're just going to subtract how much they put in, and that'll give us our total amount made. So it looks like they made about $5,200. That's pretty good. But we need to calculate the fact that they made $5,200 over 17 years. So there's a little bit more math to do, but what you need to do is recognize that that's not the total return. That's the total return of dollars. But if we want to do the total return in percent, we'd have to say, well, 5,200 divided by the original investment. And that would give us their return on their investment. But again, that's not taking into account that it happened over 17 years. So when we get our investment, we need to take into account that it happened over 17 years, which means there's 2 ways we can do it. I think what we should do is we should do the geometric mean. Okay, in other words, we're going to take the 17th root of our gain there. And that should give us what we're looking for. So if we take 1 plus, let's figure out what this final number would be. 5,200 divided by 5,900. So that's 0.88, let's say 1, or 88.1%. That's a good return. That means that's 1 plus 88.1%. So that means we're going to take the 17th root, of 1.881, and let's see what we get. If you don't have a calculator that can do 17th root, that's something that you might come across, then what you can do is you can actually use exponents, and the 17th root is the same as saying 1.881 to the 1/17th. So some calculators can't do 17th root, but they can handle exponents like that. And so according to my calculation, I got the number of about 3.8% return annually.